All right, so before we go anywhere else, let's try and take a look at our initial mole concentrations. So remember how we talked about extensive reaction and initial concentrations? Well, if we have 100 moles as our basis of calculation in our feed, and we have 10% of that is C3H6 propylene, then that means that initially we start with 10 moles of propylene in our system. Same thing goes for ammonia. If you have 12% in a 100 mole feed, that means you have 12 moles of ammonia. Now, a little trick here for this problem, and I would let you know that this is how you need to do it. If you have 78% air in the system and only 21% of that is O2, you can multiply that 0.78 times that 0.21 times the 100 moles to give you 16.4 moles of oxygen starting in the system. Now, on an exam, I would give you this 0.21, and I wouldn't expect you to know what the composition of air is. All right. So that's where that comes from. That's the composition of air. All right. So from here, we want to determine which is the limiting reactant. So we're going to take what we know. We know initial concentrations of B, A, and C. Okay. And what's coming in is related to B and A for the most part, right? So that O is related to air. We're always pretty much going to have air in the system. So we're really kind of just looking at B and A. So remember, B is ammonia, A is propylene. So if we have 12 moles starting of that NH3 and we have 10 moles starting of that C3H6, that means we have a ratio of 1.2. Now, if we look at the stoichiometric ratio, the coefficients are both 1, so that's a 1-to-1 relationship. So what we see here is that NH3 is in excess of C3H6 propylene in this case, right? So what does that mean? That means that propylene is our limiting reactant in this particular scenario. And that's important because we need to know what the limiting reactant is. All right. We should also do a check, right? We should do a check on oxygen as well, right? Because we can't assume that just because it's air and it's always going to be continuous that it's not limiting. So let's just make sure we do that check. If we do air or oxygen in relationship to propylene, we have 16.4 moles in relationship to 10 moles. That gives us a 1.64 ratio. If we look at the stoichiometric ratio, these are the coefficients, right? So the 3/2 comes from the O2, the 1 comes from the propylene. So that ratio is 1.5. So what that tells us is it tells us O2 is in excess of propylene because 1.64, is greater than 1.5. So what that means is that by checking both of the other reactants, we know that our propylene is our limiting reactant because it's present in less than its stoichiometric proportion, that's a big word, with both O2 and NH3. So that's our limiting reactant, right? So if you remember back here in our problem statement, right, we need to know what's reacting and what's the limiting reactant because we have a fractional conversion of the limiting reactant. So you have to know which one it is before you can use this 30%. All right, let's keep moving. So we're going to want to determine the excess of the non-limiting reactants. That's part of what we need to do for this problem. So we're going to need to find stoichiometric ratios and numbers related to both B and C, what's coming into the system. So if we react 10 moles of propylene, right, that's your Na naught. For every 10 moles that you're reacting of propylene, if we use the stoichiometric ratio, we're going to consume, right, 10 moles of NH3. If we started with 12 moles of that ammonia and we reacted 10 moles of it, that means we have 2 moles in excess. So here's what happened, right? We said, okay, for every 10 moles of C3H6 we react, we have 1 mole consumed of ammonia per every 1 mole consumed of propylene, which means that we have 10 moles of NH3 that were consumed. All right, so then if we started with 12, subtract what was consumed, 2 in excess. That's where that comes from. All right, if we react 10 moles with oxygen, same idea. 10 moles of oxygen times the stoichiometric ratio between the two. So instead of using 3/2, I'm using 1.5, which means that we have 15 moles of O2 in excess. So that's how many were reacted in that system. Now we need percent excess. So remember, percent excess is going to take the N amount, that's the actual amount, minus the stoichiometric amounts to find what's in excess. So we know that we start with 12 and that the stoichiometric amount is 10. So we have 12 minus 10 divided by 10, right? So this is NB naught and this is NB stoic. These are from that equation that you have in your notes. That means we're 20% in excess of NH3. Same thing if we go to O2. If we have this a little clear here, let me make that clearer. 16.4, I'm not sure that did the trick, but 16.4, right, is what we actually have. 15 is the stoichiometric amount. So if we take the difference of the two, divide it by 15, multiply it by 100, we're 9.3 in excess of O2. All right, in that particular system. All right, now the last thing that we need to do is look at conversion. So if we have a 30% conversion of your propylene into products, this is where we need stoichiometric ratios again. So if we have 30% of this influent stream being converted, there's the 30% times the total number of moles. We're going to have 1 mole of this acetonitrile generated for every 1 mole of propylene. So we're going to get 3 moles of this acetonitrile generated, and that's our ND that comes out. Same thing here, but with a different stoichiometric ratio for water. That's going to use 6 moles of H2O generated on the outflow. So if you want to go through and look at the rest of what the products would be, these are just the 2 product gases, right? You'll still have a little bit of each of the reactants because we don't have 100% conversion, but these are just 2 example calculations. So that's going to finish us out for this particular example. We'll go over some of these concepts in class.